Good morning and welcome to Ergänzungen zur klassischen Physik. My name is Tobias Osborne and I'll be taking you on this journey through classical mechanics and through to mathematical physics. Now these lectures will be videoed and uploaded onto YouTube. You can expect to see these videos about 1 day to 2 days after the lecture takes place. And you can find them on my YouTube channel, which you can find simply by Googling my name and YouTube. So we're going to look at a topic, a very fascinating topic in physics and mathematics, and that is if you like, a grand generalization of classical mechanics. It's the underlying mathematics of classical mechanics, but sort of more surprisingly, this topic of this course, symplectic geometry, turns up in a variety of other places. So this is the reason why we're going to look at this thing, because this mathematics that we learn here is somehow lying in the background of a large number of topics in physics. So if you can learn about symplectic geometry, then you'll see applications all the way from classical mechanics and geometrical optics through to relativity theory, general relativity, and even indeed into quantum mechanics. So we'll see, hopefully by the end of this course, that symplectic geometry, that even quantum mechanics can be thought of as a symplectic theory. So that's why we're going on this journey, because it's the mathematics that underlies so many of our physical theories. And then when you see this unifying mathematics, then it allows you to transfer ideas from, say, geometrical optics all the way through to quantum mechanics and vice versa. So this is a very powerful tool set that we're going to learn, and we're going to gain huge insights into the structure of physics. Now, I suppose before I get into any part of the subject material, we'll cover the most important questions. If you want the Prüfungsleistung for this course, that will be an oral exam. Just contact me for an appointment. If you want the Studienleistung for this course, then you need to achieve greater than 40% in the assignments. There will be, I think, 6. I think there'll be 6 weekly assignments. There might be 5. But I believe we'll set it at 6 weekly assignments that count for the Studienleistung. Achieve greater than 40% on those, and you get the Studienleistung for this course. For the viewers who aren't in this course, the problem sheets, I will distribute them on my blog. You can find them on StudIP, but the solutions will not be distributed. All right, so that's the important stuff if you want to get the marks for the course. Now, when can you even sit in this course? Well, you're welcome to sit in this course whenever you want, but I'm going to assume that you know some stuff. And if you don't know it, then either please go and learn this stuff pretty quickly, or accept that it's going to be a little bit require a little bit of background reading as the lectures go. So it's an absolute fundamental prerequisite for this course that you know classical mechanics. You all do, I know this. And in particular, I want that you know what on earth is a Lagrangian. I want that you know the extremal or variational, extremal principles. I want that you know what a Hamiltonian is and Hamilton's equations. and Poisson brackets. So as long as you've seen those words, in your classical mechanics studies, then you should be good. There shouldn't be any difficulty in the physical background. There is a little bit of mathematical background in this course, and that is, I'm going to assume that you've met some aspects of topology. So you know the words open set, you know the words closed set, you know the word compact, and if you don't, then you're willing to go and look these words up. So open, closed, compact, continuous, and homeomorphism. These are the only words that we'll probably use in this course. So these words will appear, but don't be too afraid. I mean, the first lecture, this is going to be a real drudge, the first lecture. We're going to have to just toil through some definitions before we can get really started in this course. And that may look a bit off-putting. We're going to use a lot of these words in the first lecture. But the beauty of physics is that physics isn't about general mathematical theories, it's about examples. And as the course goes on, we'll focus more and more on examples. I mean, wide classes of examples, very important examples, but nonetheless, it turns out we'll hardly need any of this language as the course goes on. You also need to know a little bit about differential geometry. So hopefully you've heard the word manifold. We're going to completely redefine everything in this course, but it would help if you've seen this stuff before. So it would help if you've heard the word manifold before. Maybe tangent vectors. This kind of stuff you've probably met in various ways throughout your studies anyway. If not, again, you'll get actually references to look these things up at your leisure. That's the prerequisites. We got some texts for this course. We do not follow one single textbook. There is no really one good textbook on this. So that's kind of annoying, but that's just life. We have to put this course together from various books. Now, ultimately, the best text to follow is that of Arnold on the mathematical methods of classical mechanics. This is really the canonical reference for this subject matter. It starts out super basic, this book. You learn about Lagrangians and Newtonian mechanics and so on at the beginning of the book. We'll sort of, the subject material in this course will be sort of starting about halfway through the book. So if you're a bit unclear on things. However, the really big shame about this is he uses a slightly different way of defining manifolds and charts and so on that will be incompatible with the rest of this course. So we're actually not going to follow this book directly because all the definitions are just, they don't follow the same standard forms that we'll see in all the other books. So I've decided not to follow this one directly. But this is the book that really underlies this course. Please do obtain it or take a look at it. For the first part of this course, we've got to get through some definitions to get sort of into the subject material. And for that, we're going to follow the book of Nakahara. This is Geometry, Topology, and Physics. It's a good book to have in your bookshelf if you want to stay anywhere in the subject area of physics, or even to some extent neighboring areas like chemistry, biology, This is a useful book to have. And for the large part of the second half of this course, we're going to use a very lovely book of, Canasta Silva, or Canada Silva. So if you like, the course is somehow pieces of all these three books pasted together in hopefully a coherent fashion. So you would do well to obtain all three books and use them as background reading. There's other books that are somehow indirectly used in this course, which you can look up at your leisure as well if you're interested to get a little bit more background. All right, that's the sources, the prerequisites, the assessment. All right, then let's look at the topics we're going to cover in this course. So the first topic that will occupy us for a couple of weeks is a reasonably comprehensive review of differential geometry. We're just going to have to work through those definitions and do some examples and exercises in order to get comfortable with this language. Then we'll get on to the objects that will interest us for the rest of the course, namely symplectic manifolds. We'll be able to talk about those after we've introduced differential geometry. And then at that point, I guess we'll talk about the Darboux theorem. And then Hamilton mechanics in the context of symplectic geometry. So and then, hopefully, we can talk about the good stuff. So moment maps, a vast generalization of Hamiltonian mechanics. And then a really remarkable result in this field, which is a theorem or a bunch of theorems due to, I think you say, Dijkstermaat and Heckman. That's the objective for the course, to see these things, to cover these topics throughout this course. So this is a course in a physics department, not a mathematics course. So what does this mean? It means that we're going to talk, although this material is completely mathematically rigorous, there's no point in this course where I'm going to wave my hands and say, you need to know some physical intuition to get to the next step. Everything here in this course, all this material can be proved at the level of mathematical rigor. Although all that is true, we're not going to prove things at the level of mathematical rigor. So that'll allow us to get through the material quicker, and I'll appeal to examples often in order to establish results. So So the proofs in this course will usually be in the form of a proof by example. So we'll look at an example where we can check everything and see how the proof works. And then we just leave the kind of more abstract formulation of the proof either to your background reading, and I'll definitely be able to give you a reference for every proof. Or indeed, we might just prove things using more physical sketch arguments than going through all the little steps of a proof. So that's the kind of level of this course. This stuff is all rigorous, but we're not going to cover it at the level of a mathematics course. If that's what you want, then the math Institute does have courses at your disposal to learn this stuff more rigorously. And the emphasis here will be on applications to physics. Right. So I think that covers all the sort of boundary conditions, background material for this course. Are there any questions before we proceed? No? So, oh yeah?
Is there going to be a UBO?
There will be an exercise class. It will occur in the 3-in-1 format. So we'll have 2 lectures in 1 week. And then next week, we'll have 1 lecture on Thursday, and then the exercise class on Friday. And then again, this periodicity continues, 2 lectures, then 1 lecture, and then an exercise class. It might be that we move the exercise class from Thursday to Friday, depending, but at the moment, this is the current plan. And yeah, the lecture notes will not be distributed for this course. That's more also for people watching. The notes for this course are handwritten, and indeed, as I go along, I often change what's written here. And so the canonical notes for this course are what's written on the board. So you have to watch the videos or write them down if you want the lecture notes. Why symplectic geometry? I mentioned this before. This is why we care about symplectic geometry, because it's the mathematical formalism underlying all these areas in physics. If you like, it's a unifying formalism. And we like unifying formalisms. I mean, you shouldn't become obsessed with unifying formalisms, but when you have a good one, then what it'll do is it will allow you to take ideas and tricks you know in one area and apply them to get results in another area. And so that's why we like formalisms, and when they're good, that's what they do, right? They give us ways to solve problems in one area by using tricks from another. It also simplifies things. When you have a good method underlying formalism, not a bad one, there's no shortage of formalisms out there, but a good one allows you to compress what you need to learn. It allows you to reduce the surface area of the stuff you need to remember. So when you learn physics for the first time, it looks like just a vast array of, a heterogeneous array of different methods, different theories, different techniques, and so on. And as you go through your physics training, you learn that there are principles underlying this heterogeneous collection of ideas and methods and so on. And then as you go even further along, you start to see sort of the bigger abstract picture of what's underlying everything. And so you could make a pretty good argument that symplectic geometry is one of the bigger abstract structures underlying physics as a whole. Now there's gaps in this list, right? There's nothing about statistical physics here, although we could put that there. There's a sense in which symplectic geometry underlies statistical physics and thermodynamics. There's places where it doesn't work, at least not very easily. It's usually in systems with dissipation, friction, loss, noise. Well, it's not entirely true. So I should say where it doesn't work so well. Not so good for That doesn't mean to say that you can't apply it in these settings. Indeed, sort of recently, I was delighted to learn that you can apply symplectic geometry to study systems with quantum noise. So that doesn't mean it's not, it doesn't somehow live there, but it's just not as useful for these sort of systems. So if you're interested in physics of very noisy, very lossy, very systems with loads of friction, then probably symplectic geometry isn't the formalism you'll run to solve your problem. You'll go for a different way of setting up your problems. But if you're interested in closed systems, then if you take the little bit of extra effort to phrase everything in with the language of symplectic geometry, then you might find that if you came up with a result that you could actually generalize it to many, many other places and learn many more things. So we like formalisms because they reduce the surface area of things we have to remember, because once you know the formalism, then every other one of these topics just becomes an example or an application of that formalism. They help us to learn things, but it's not always, it's not the, like, this is not the silver bullet or the panacea for all problems. All right, the objective for today, well, the next couple of lectures, is to build up enough mathematical background to talk about these things. So brace, brace. The next couple of hours of this course, we're going to be writing down definitions. And that the reason we're going to do that is to give us enough background to actually start talking about interesting mechanical systems, ones that model these settings here. And then we're going to use this more general mathematical background to introduce the things that really underlie everything, which is symplectic manifolds. So I estimate sort of by lecture 5 or 6 we'll be onto symplectic manifolds. And for the next 3-4 lectures, our first definition is by far the worst definition in the entire course. If you can hold on for this, then you'll probably be good. We need some mathematical way of talking about the things we want to talk about. This is the most general way to do it, and we're going to get more and more specific until we really just focus on examples. So this is like, looking at Euclidean space and then generalizing that beyond the point of recognition. But it's not so bad. The most general things that lie in the background mathematically for this entire course are things called locally Euclidean spaces. So even before I write the definition down, let me just tell you in words what this is meant to capture. So we understand Euclidean space, n-dimensional Euclidean space. It's a very beautiful place to be. You can do calculus there. You can translate objects there without any kind of weird curvature effects. It's just a nice place to be. So it has lots of extra properties that we use, maybe unconsciously or consciously. And we want to generalize that to the kinds of spaces that we encounter in physics, particularly in relativity, general relativity. There we know that space isn't Euclidean. There's curvature, and indeed it's not even Euclidean, it's Minkowski or Lorentzian. And you want to generalize those things that work really well in affine Euclidean space that you know and love so well to this more general setting, but you don't want to lose too much along the way. So the thing that you try and do is you try and say, okay, I'm going to give up on spaces that are globally Euclidean, globally flat everywhere with a coordinate system that's nice and rectangular. I'm going to give up on that and instead consider things that are the next best thing, right? Things that look like Euclidean space locally. If you're a little ant living in this space and you look around, it looks like Euclidean space. But globally, things can be different. So that's the most general objects we're going to consider in this course. So in words, a locally Euclidean space is something that locally looks like normal flat space, but globally not. Okay, that's the definition here. Locally Euclidean space of dimension d is a Hellstore topological space. Okay, those words you may or may not have encountered. Now, if you haven't encountered them and you don't want to encounter them, then just think sufficiently nice is the physicist's way of translating Hellstore topological space. It means to every 2 points you can put little circles around them, if you like, that separate them. For which every point in this space has a neighborhood. That's also a technical term. I'm going to underline the technical terms. Neighborhood. Homeomorphic to an open subset of RD. So that's the way of capturing this physical notion that every point looks kind of like Euclidean space. And kind of like here is captured by the word homeomorphic, which just means continuously. There's some continuous map from some region around the point to some bit of Euclidean space. So if you can sort of hold on for that definition, then it gets sort of successively better, I hope, in this course. Yeah, I guess I'll draw the picture already. This is a locally Euclidean space. What does that mean? It means that every point in this space is a little neighborhood where this neighborhood can be continuously deformed into some nice subset of R to the D. So every point in this neighborhood has an image here in R to the D, and it's also a continuous map. So the map that connects our locally Euclidean space M, this most general object, to R to the D, we're going to give that the name phi for the moment, and if phi sorry, I'm just going to change the notation slightly. I don't want to name the open subset we end up on. We'll just say homeomorphic to an open subset of R to the D. I want to name the neighborhood here. So that's the U. So if we have this map that takes this region around this point P to R to the D, then that map has got to be a thing called a homeomorphism. It's a continuous map with a continuous inverse, and it's called a coordinate map. So that's how we call these things. And this map is pretty cool because it gives us some functions on our locally Euclidean space. And those functions are what we would call like the coordinates. How does it work? Well, you first go from your locally Euclidean space to R to the D. And then you've got some really well-defined functions on R to the D, namely the coordinate functions. You know, they tell me the jth coordinate of this point. That's what that means. And so this map goes from M to R, and this map goes from R to the D, and this map goes from R to the D to R. So we've got a map, Q, which goes from M to R. It's easy to get lost in differential geometry. Maps are going this way and that way and inside and outside. And so it's always worth just thinking through where does it go and where does it come from, where is it going to. So given these Q's, you can draw a grid or a coordinate system on M. You just define them to be the surfaces of constant Q, just like you would use the coordinates in Euclidean space to draw a grid on flat space. The grid is defined by surfaces of constant x, y, and z, and so on. So that allows us to build up a coordinate system on our locally Euclidean space. So I'll draw the picture again. Here's the locally Euclidean space. M, here's a point P. Here's some region U around it. Here's R to the D over here. Here's the map phi. And now, this line here, which is the line of the x-axis, say, the line of 0y and 0z, that has a pre-image, right, up here. So maybe it looks like that. It gets a bit distorted by this map. And then the other axis here gets also distorted, and so you can find something that looks very much like a coordinate system here, but it's a curvy coordinate system. And furthermore, you can, if you had a nice grid subdividing RD into a lattice, then that lattice would have some curvy pre-image here in this locally Euclidean space. So that's like almost as good as Euclidean space. Every point here has like a coordinate, which is a list of numbers. It's a list of D numbers, in particular these. Every point in M, sufficiently close to P. But of course, there's a problem. This coordinate system doesn't necessarily extend to the whole of the Euclidean space, of the locally Euclidean space. So it's a good coordinate system locally, but if you try and extend it all the way around, then you might encounter problems. Now, there's an example, like your classical example that we're going to return to throughout this course is the circle or the sphere. This is a great example of a locally Euclidean space. Let's just take the circle. We're going to come back to it anyway. This is a locally Euclidean space. I think this is part of your first exercise sheet to do this properly. So I'm just going to do a really vague hand-wavy argument here. Circle, is it a locally Euclidean space? The answer is yes, of course. So here is the circle. Let's just pick a point on the circle, say here. Is it homeomorphic to an open subset of R? Well, yeah, indeedy. All right, just take some interval around your favorite point. There is a map. Phi that identifies each point on the circle with a point in R, like this. Can we extend this map all the way around the circle? Well, almost, right? You can get it all the way. You can extend this interval all the way up to like just before these endpoints of the interval meet. But what happens then? Pop, they join. And that map becomes not invertible if you try and cover the whole circle. So the circle is locally Euclidean, but not globally Euclidean. The minute you try and extend this identification with a real line to include the last point on the circle, the map does not become invertible and is no longer a homeomorphism. So that's the example. You have to think about these things a bit more carefully in the homework sheets, but there's the moral. All right, so those functions are called the coordinate functions. I got a bit distracted. Or say a pair. So such a pair of a neighborhood in M and map to the R to the D, that's called a coordinate system. Or, if you're a mathematician, a coordinate system or a chart. Sorry, if you're a mathematician, it's a chart. If you're a physicist, it's a coordinate system. Good. Well, we got through that. It's not so bad. So Richard Feynman had many tricks to looking clever. One trick was in any talk or any lecture, he would keep a very simple example in mind and test everything the speaker was saying on that very, very, very simple example as the talk proceeded. And then at some point in the lecture, he might notice an incompatibility with what the speaker was saying and this extremely trivial example. And then he'd ask some question that would seem extremely deep, as though he understood the entire material of the lecture. Of course, what he had noticed was an incompatibility with a simple example and what the speaker was saying. So I highly recommend that for the rest of this course, that you keep the simplest example of a circle in mind, and that'll give you the power to ask difficult questions when we get to more general theory. Certainly it's the example I always keep in mind when hearing about anything to do with symplectic, with differential geometry. Turns out the circle is not really quite the best example for symplectic geometry. As we'll see, there's a kind of a natural one, the cylinder. We'll get to that, but for this part of the course, the circle is a really good Feynman example, if you like. Now, up to this point, these maps phis are just homeomorphisms. That means they're just continuous. Continuous maps are ghastly things. You don't want to live in the category of where the morphisms are continuous maps. These are vile, vile things. All kinds of horrible maps can be continuous. Cantor staircase functions and blah. So continuous is not the place we want to be in physics. Nothing in physics leads us to think that it's continuous but not differentiable. Usually you can make a small change and it responds in a way to the small change. So we're going to get as quickly as possible away from a category where we need to talk about continuous maps. I mean, it doesn't mean that the maths isn't interesting. It's a super duper interesting part of maths to study local Euclidean space where you only have continuous maps and all kinds of crazy fractal stuff can happen. It's pretty nice, but it's not really relevant for physics. So let's throw away all those pathological examples. And demand that everything starts to be differentiable so that we can take derivatives and not have them explode in our face. So a differentiable structure f of class C to the k on a local Euclidean space some extra structure that we're going to put on top. What is it? It's a collection. It's a bunch of charts. I just write charts instead of coordinate systems because it's sort of shorter to write the word chart than coordinate system every time. Of charts. It's a bunch of charts now. Not just one anymore, but lots. U alpha, phi alpha. And these alphas are running in some indexing set A. It might be a finite set, it might be an infinite set, it might be an uncountably infinite set of charts. So it's a bunch of charts satisfying some extra conditions. So condition 1, well, nothing's missed out. This is the simplest possible requirement we could have of a bunch of charts. Every point in M appears in at least one chart. So we're not going to miss out any points. That's a really, I think, mild thing to require of a bunch of coordinate systems, is that at least we can assign coordinates to every point, maybe not in every coordinate system, but at least in one coordinate system. And here's the more important one, that is that these charts, these coordinate systems are in some sense smooth enough that we can take derivatives. And that's what this next condition tells us, that phi a alpha composed with phi beta inverse is k times differentiable. See, k means k times differentiable. It doesn't mean the constant c to the power k. It really means k times differentiable. And there is going to be one extra condition that will look completely bizarre, but I'll try and explain why that's there. All right, third condition. All right, this collection of charts is maximal. You can't add in another one. So this is not the way we usually do differential geometry in physics. Usually in physics, you just get enough coordinate systems to cover your space. Like the circle, you only need 2 coordinate systems, as it happens, to cover the whole circle. And then you just do maths and calculations with respect to these 2 charts. But a differentiable structure, what is it? Well, it's not only those 2, but any other one that's compatible with those 2. You have to add them in. That seems like unnecessary baggage, but it's there so that you get a unique object out at the end. Otherwise, you don't have a unique way of talking about the differentiable properties of this circle. So this is like nitpicking. We're never going to use this third condition, but we're going to write it down. So it's maximal with respect to the property that if a chart has that these functions are c to the k, namely these charts are sort of compatible with all the other charts that are there, then you have to add it in to this differentiable structure. So remember, a differentiable structure is a bunch of charts, and it's a bunch of charts that's so big that you can't add in an additional chart because it already contains all charts that are compatible to the level of k derivatives. Now we're going to instantly forget this third condition. You have a question?
Yeah, you say that we have a different structure and we can put so many charts here that we have the maximum collection. But if there's a possibility that we have two differential structures, like we have a chart and another chart, they are not compatible?
So the question is it possible to have two differentiable structures? It sure is. Manifolds can have, locally Euclidean spaces can have different differentiable structures. That's sort of, particularly when k is low. When k is like 1 and 2, you can get different structures. I will leave that as a very challenging exercise. This is not trivial. I think phi cubed, hang on. I think the real line can have, if I remember it correctly, the real line has more than one differentiable structure, and the map is like phi x cubed or something that gets you from one differentiable structure to another. That's what I have in my memory as being the example. I see people nodding, so that people obviously more familiar with this material than me seem to agree. That's good. Now, as I said, we're going to make this condition, then we're going to throw it away. We're not going to think, because we're always going to work with just one or two charts. And why does that work? Well, once you've got a couple of charts, then you just keep adding in until you can't add in anymore. So you more or less specified a differentiable structure once you've specified charts that cover a manifold. Oh yeah, and what else are we going to assume? Well, we're going to assume that k is infinity pretty much throughout the entire course. But, and I want to stress this, in physics, our equations of motion are usually second order or lower. So actually, everything we could say could be maybe true at the level of second order differential equations, or even first order. If you go to weak forms and fluid mechanics and stuff, you might be able to specify all your equations of motion using only one-time differentiable functions. I mean, life gets very complicated around there. And boy, do things get interesting when k is 1 and 2. So when k is like 3 and above, stuff starts to get pretty boring. But around k is 1 and 2, where you have continuous functions and just one-time differentiable functions, then you can get all kinds of different structures. But I'm just quoting that as an interesting thing to keep in your mind, that nowhere in physics does it really say things have to be infinitely differentiable. That's us wanting to make our lives simpler. And indeed, certainly if you think in terms of fundamental physics, it's like not even clear that things should be differentiable at all. If you take seriously the idea that the holographic principle, for example, then the space-time itself should be comprised of a finite collection of degrees of freedom. And that's not even continuous, differentiable. I mean, these concepts completely break down at the Planckian level. So this is all an approximation to perhaps discrete things lying under the surface. So, but as I said, for this course, we're assuming k is infinity. Maybe it's important that k is only 2 in some parts, but I don't think so. All right, another piece of terminology. A collection of charts obeying 1 and 2. That's right, isn't it? Yeah, yeah. It's called an atlas. And the reason it's called an atlas is because that's actually what you see in an atlas. When you open up an atlas of the Earth, then on every page you see a piece of the Earth, right? That's a coordinate chart of the Earth. And these coordinate charts are, they smoothly depend on each other. You turn the page and see another part of the Earth. And then if you turn the page backwards and forwards quickly, you can sort of see how one point on the next coordinate chart is mapped continuously or even differentiably with a point on the previous chart. So, you know, that's a really nice definition because the word here evokes exactly the content of the definition. So I'd certainly be remiss if I did not draw the picture of underlying this definition. Here's M, our locally Euclidean space with differentiable structure, F. And the pieces in this definition are usually illustrated in any book that you care to obtain in the following way. So we have a U alpha, we have a U beta. These two neighborhoods intersect. They have a non-trivial intersection. Now what is a coordinate chart? Well, it's a map phi alpha from the neighborhood to some nice Euclidean space. And I'm going to color in this bit that's common to these two charts. And so that bit looks like this in this coordinate system, this chart here. And then this chart here is also mapped onto another Euclidean space, another copy if you like, by phi beta. And now let's look at this thing here, phi beta inverse composed with phi alpha. What's this thing doing? Well, that's a map. Well, what is it a map from and to, right? This is very easy to get confused in differential geometry, so we do this slowly and carefully every time. That's a map from R to the D, in particular, this R to the D. Well, phi beta inverse goes from R to the D to M. And then, well, where it's defined, I mean, it's not defined here, it goes then back to R to the D again. So this is a map from R to the D to R to the D. And we're demanding that this map is k times differentiable, or, since we're making this assumption, infinitely differentiable wherever it's defined. That's what we're demanding. So in this little colored in patch here, so on this colored in patch here to here, oops, there's got to be an inverse. Oh, it really doesn't work. That's got to be a super smooth differentiable map. And as I said, you look in the atlas, you open it up, and you see Germany in the middle of the page, and then it sort of, the page ends around France, and then you turn the page, now you see France, and you see a little bit of Germany, right? There's this overlap between that page and the previous page. And it's a good atlas because the bit where it overlaps is mapped nice and smoothly between the pages. That's these overlap or transition functions. And I think we're going to end the lecture over the next half an hour with just a list of examples. So a definition is a good definition if it captures all the examples you want it to capture and maybe a couple more. It's a bad definition if it doesn't capture all the examples you want it to capture, or if it's so general that anything can satisfy the definition. So mathematical definitions is a kind of a Goldilocks zone, not too cold, not too hot. They just capture enough of the examples, but not too many and not too few. So to prove to you that this definition captures the examples we want in this course, and well, it's difficult to show that it doesn't capture too many, but it's certainly that it captures enough, I'm going to go through some examples. And these are the most important examples for this course. Yeah, I guess I'm missing out one example that's really important, but that's about it. So, what is all this stuff meant to generalize? Well, Euclidean space, so it better be the case that Euclidean space itself is an example. If not, then wow, that was a really bad definition. Okay, well, yeah, it's a... Sorry, I forgot to write down the main definition of a manifold. So before we can write down the examples, I've got to tell you what a manifold actually is. And it's kind of clear, right? We have this locally Euclidean space, we have differentiable structures, so a manifold is presumably something that's got both. All right, here it is. So a d-dimensional manifold What is a d-dimensional manifold of class C to the k? Well, it's got to be a locally Euclidean space with a differentiable structure of class C to the k. All right. There's one technical term that's sneaked in there in this definition, second countable. No examples we consider will get anywhere near not second countable. Second countable is like a technical condition that allows us to do integration on these manifolds. It's really difficult to think of not second countable examples, but if you want to knock yourself out, there's a book called Counterexamples in Topology that'll show you no shortage of examples of not second countable locally Euclidean spaces. And I think this is like sort of required reading, a book like this. In your scientific career, it's really vital that at some point you look at a book with the title Counterexamples in X, because it just shows you what happens if you're not careful with your definitions. So if you make a definition and you think that you can draw conclusions from that definition because this definition captures all the examples you know, right, and you know how these examples work, then you can be led to dangerously down the dangerous path of making wrong conjectures or even not being able to prove things. And so these books, they present like the most pathological, evil things that satisfy various definitions. And you know, you think you might have a good imagination, right? Because you can think up of like Harry Potter or something. But you know, the people who write these books, they just live on another dimension. It's just absolutely mind-blowing what's in them. So that's why it's second countable, because really bad things go wrong if it's not. But it doesn't matter, because for us, as I said, physics is about examples. You know, we know the Hamiltonian of the universe, more or less. We don't need to consider all the different Hamiltonians. Yep, question?
So what does second countable mean?
I don't remember, is the short answer to that question. What does second countable mean, was the question. A finite. It's the one that says there's dense. A finite basis for a.
No, not finite, but countable. Maximal countable.
Maximal countable basis. That. So in topological spaces, there's various different restrictions you put on them, T0, T1, T2, T1.5, and so on. And they're all additional constraints that you put on the definition of a topological space. And I'm afraid I get lost somewhere around the second countable point and have to look it up in the book. Now we can get to our examples. So as I said, right, is it a good definition? Is it a bad definition? Well, it at least better capture that one example that we started off with, namely Euclidean space. Well, it is a manifold. And it does actually have an atlas, a really simple atlas, the world's simplest atlas. Well, U equals R to the D, and the map phi is the identity. So that's a super good coordinate system for this space. Done. Right? It's a and then you can add in all the other charts to make a differentiable structure. So good. This definition, while a mouthful, does capture the basic example of our course. Does it capture everyone's favorite second example, namely the Earth itself, the surface of the Earth, which is a sphere? Well, you can see the whole terminology is adapted to this example, from this example. And yes, indeed, the sphere is an example of a two-dimensional manifold. And so there's an atlas given by stereographic projection. So you take this is R2 here. And you put the sphere underneath it. And then you sit on the south pole. And then you draw a line through the sphere. It intersects the surface of the sphere somewhere. and then you continue that line up to when it hits this R2, which is sitting on the north pole. And so to every point except the south pole has an image in R2 under this mapping. This is what we'll call phi 1. So that's a chart, right? You can check that it's infinitely differentiable except at the south pole. To make it an atlas, we need to be able to cover the sphere at least with one other chart. And the second chart that we use is just the same idea, but done from the north pole. So I have a second chart, a mapping that goes, you stand on the north pole, you draw a line through the sphere until it hits the surface, and that point gets identified with where it lands on the R2 on the bottom. And that's called phi 2. That's an infinitely differentiable map from the sphere to R2. The sphere embedded in R3 as it happens. Because if I didn't say the word embedded, then I would have said something wrong. Because the only thing we need to check is that where these two maps have a common domain, that the transition map is infinitely differentiable. The maps themselves need not be differentiable in any sense. In fact, to make sense of the word differentiability of such a map, we're going to have to do a lot of extra work. But for this example, it's embedded in three-dimensional space. We can sort of cheat. And this is an example. It's part of your exercise to work out that this is a manifold of class K is infinity. All right, then in the last minutes, I'll mention a couple of other examples. Let's choose some examples that apply more to mechanics. I'll go through a couple now. So the planar pendulum. So the configuration space of a planar pendulum is a manifold. Well, we've already done it actually. So if you have a planar pendulum, then it's with a rigid weightless rod and a mass, no friction, blah, blah, blah. All the conditions that you like. The configuration space of a planar pendulum is a manifold. And the manifold, of course, is just S1. That wasn't too hard. Then the planar double pendulum. Its configuration space is, well, not S1, but S2. S1 cross S1, the torus, T2. So I haven't proved that this is a infinitely differentiable manifold. That's an exercise for you. But once you see the sphere and the circle, then you can start to imagine, I hope, how those arguments work. Here's a sort of more interesting one. Imagine a dynamical system consisting of a rigid line segment that's stuck in the plane. So it's a little piece of infinitely thin, it's an infinitely thin rod of some finite length in the plane, like this piece of chalk, right? And it moves around the plane. How many coordinates do you need to specify the configuration of such a thing? Any takers? So this looks like a coordinate. That looks like a coordinate. Is that enough? 2? 4 coordinates is one answer. Do we need 4 coordinates for the rigid line segment in the plane? Well, we definitely need x and y. It's 2. We also need rotation. So that's a third one. But I think we don't need a fourth one. Because you're right in that to specify both endpoints would require 4, right? If you have a rigid line segment, you could specify it with 4 coordinates, namely the coordinate of this end and the coordinate of the other end. But there's an equation of constraint here that the points are always a certain distance apart, so that cuts it down to 3. So the rigid line segment, the configuration space M, is actually equal to R2, the plane, its coordinates of one endpoint in the plane, plus a rotation. That's a manifold. And actually, the quantum theory of that is not that far off the quantum theory of strings. So these kind of manifolds, they look a bit trivial, but they can get rapidly very, very, very complicated. Do I have any more examples for you today? I'm going to give you a 6th one. Hilbert space is a manifold. It's a bit weird. You don't usually think of Hilbert space as a manifold, but it is. And actually, it's a Kähler manifold. That's something that we may or may not see in this course, which means that it's a symplectic manifold. And that's why quantum mechanics, it's sort of an underappreciated fact, why quantum mechanics itself is symplectic. It's covered by the formalism of symplectic geometry, so at least in finite dimensions. Hilbert space of an infinite dimensional system, sure, that is a manifold, but it's an infinite dimensional manifold, and we're certainly going to stay away from those in this course. Although, to be fair, a lot of what we'll deduce will be just simply true for the infinite dimensional case. I want to end with a nice way to construct examples. And really, this is the way I think this is the way most people think about manifolds anyway. Right? So there's this lovely abstract definition here, locally Euclidean space, homeomorphisms, transition functions, and so on. But really, if we're brutally honest, the way we work with manifolds is we usually find some bigger space, which is a clearly like Euclidean space, and then we realize our manifold is some surface, some embedded space. And then like all this abstract stuff isn't really necessary. You just do your usual Euclidean thing, but with some constraints. It's pretty rare that you have to worry about Klein bottles or Möbius strips in physics. Pretty rare. Like it is possible these things come up occasionally, but usually the manifolds in physics we care about are actually embedded, actually live inside something else. All right, this is a ready source of examples. And pretty much all the examples we cover in this course will be really embedded manifolds. What are they? M is a k-dimensional embedded submanifold of Euclidean space if, in a neighborhood, in a small region around every point in your manifold, there's a bunch of functions which vanish on your manifold. That's not enough. You also need that the gradients of these functions are linearly independent. That stops some nasty counterexamples coming in. You'll see that as well on your assignment sheet. And what's a perfect example of an embedded manifold? Well, a circle, right? A circle is an embedded manifold in R2. It satisfies, there's one equation which is 0, namely x squared plus y squared minus 1. 0 on the manifold. The sphere is an embedded manifold. It's what you get when you restrict in R3 to points which obey the constraint that x squared plus y squared plus z squared minus 1 is 0. But you can come up with crazier examples. Take the intersection of the sphere with a paraboloid. There's 2 equations now that define that, and it's some like curvy circle. Try and draw that. That's one equation, f equals x squared plus y squared plus z squared minus 1. That's the equation that vanishes on the surface of the sphere. And then you want to intersect it with a paraboloid, say. That's a second equation. Let's call that z minus x squared minus y squared. That's the second equation defining a paraboloid. The intersection of these 2 things is some slightly curvy, no, in fact, it's just a circle, isn't it? It's not even a curvy circle, it's just a circle. So that's an embedded manifold as well. All right. I think that's all, I want to say today. Thank you very much.